So this is Lab 1 charged tapes. So the goal for this experiment was to determine the amount of excess charge or deficiency on a piece of charged tape. And so the fundamental principles used here are that net force is equal to change in momentum with respect to time, Newton's second law, and Coulomb's law, which states that the electric force between two charged objects is directly proportional to the charges of the objects and inversely proportional to the distance squared between those objects. So the results for this experiment were that the excess charge on a piece of tape was experimentally determined to be 1.623 times 10 to the negative 8 coulombs. And so this is how the charged tape was generated by ripping one piece of tape off of another piece of tape, the base tape. And so once we did this, we know that this U-tape is charged because it was interacting with objects around it. So it was attracted to my hand, it was attracted to the table, and then when I created a negatively charged pen by rubbing it through my hair, it was very attracted to that negatively charged pen. So that means that the tape itself was positive. And when we made two of these pieces of tape, they repelled each other. And this is expected because they would both have a positive charge, and like charges repel. And so from there, we're able to use these pieces of tape to figure out the amount of charge deficiency by holding one piece of tape underneath another piece of tape, and eventually when they get close enough, one of the top pieces of tape will look like it's floating because they're repelling each other. And so we can assume that the only forces acting in the y direction on the top piece of tape are the electric force and the gravitational force. And since there's no change in momentum in the y direction, that means that these forces are equal to each other. And so we can easily calculate the gravitational force using the mass of the tape and gravitational constant on Earth. From there, we can calculate the magnitude of the electric force because it's the same. And then using Coulomb's law, isolate the charge of that piece of tape. And so in order for this model to work, we have to assume that each U-tape has the same charge so that this Q1 and Q2 term are the same and we only have one unknown variable. And we have to treat each piece of tape as a point charge with all the charge located at the center. So this is the code that was used to create a model of this. And so the mass and separation distance are based on our experiment, with this being the separation distance between the pieces of tape. And by calculating the gravitational force and then from there the electric force, we can isolate the magnitude of the charge on the piece of tape. So as I mentioned in this experiment, we found that the charge had a magnitude of 1.6 times 10 to the negative 8 coulombs, and again, that's electron deficiency because it's positively charged. So by dividing the magnitude of the charge by the charge of an electron, we found that there were 1.1 times 10 to the negative 11 electrons deficient on that piece of tape, so given up. And using the area of the tape, assuming that the tape is a two-dimensional rectangle, we're able, and dividing that by the area of an atom, we're able to find the number of atoms on the tape, and from there find the ratio of atoms that gave up electrons, which we found to be about 1 in 10 million, or almost 11 million. And so quickly, if electrons were positively charged and protons were negatively charged, the U-tapes would just both have negative charges, still repel each other, and it would be the same magnitude charge. However, since they are negatively charged, we would have observed that it was repelled from the pen. And it's important doing this experiment not to handle charged tapes too much, because when you handle charged tape, electrons transfer from your hand to the tape, and so they decrease that electron deficiency.